Okay, so let us start the new topic, which is under the title of Combinatorics, which is actually a very fascinating subject. It has a lot of applications within the realm of mathematics, computer science, physics, more or less everywhere. Uh, you can feel some kind of relation to these combinatorics. If I want to give you an idea what combinatorics is, might be this is good to say that it is counting which without actually going through the process of really counting. So I want to know how many things are there without sitting and counting them. I just want to find the final answer. For example, I don't know, in Sweden, as far as I understand, the plates, the register plates for cars includes three letters and three numbers. I don't know if there are some restrictions, but let us say that the letters are coming from English alphabet and the numbers are coming probably not zero because that would be confused with O or something. Okay, then we want to know how many cars we can register using this system. Okay, so that's not a very complicated problem, yes. So we have, for example, I don't know, ABC for the letter part and 1, 2, 3 for the number part. I don't know if this is completely the rule, but let us say that we want to count the number of plates, car plates, register numbers that can be registered within this system. It's not a complicated problem technically, but of course that is also very boring if I want to start writing them all down and count them. Yes, of course, if you know how to write a code, I don't know, in Python, in any other language, that's not a very big problem. So you just write a code, generates a list of all of them, and then you find the length of that list, or anyway, this will give you the total number. So if you have a little bit of experience in coding, that would be a great opportunity for you to test your understanding how you can code, because these problems are extremely simple. I don't think they are very hard to code them. Okay, so that's one problem in combinatorics. So I want to know how many cars I can register in Sweden by this system. Okay, or I don't know, in personal number, how many peoples can have different personal numbers in that system, because we have only 4 digits at the end, and of course we have our date of birth in the beginning. Yes, anyway, these kinds of problems are combinatorial problems. So we want to find the total number of a group of things without actually going through the process of counting them individually. It's a very good, idea of what the meaning of combinatorics is. And then I want to warn you from the very beginning, don't blame yourselves, because the statement of the problems are extremely simple, but it doesn't mean that the solution is simple. The solution might be even very complicated, even if the statement of the problem is simple. So don't blame yourself to be stupid or something that you cannot solve the problem, because that was my feeling when I was at your age. Yeah, but so these combinatorial problems, the statement of the problems are extremely simple. Even grown school honor students can understand its content, but coming up with the solution is not that easy. So be prepared for that, and that's the fun part of the story. Yes. Okay, but in order to understand that, of course, I want to present this in a systematic way, so that at least you have something to think, so some anchors that you can rely on so that you can solve these problems better. But I will not guarantee that, okay? But you have to practice a little bit. The first thing that comes into this topic is the product principle, which when I state it, it is simple. For example, even before saying that, you have some idea. For example, let me say that we want to set up a committee, or we want to set up a team for working on a project. I want one physicist in the team and one mathematician. And let us say that there are 4 physicists are candidate for this, and 5 mathematicians. Yes. So 5 mathematicians are there. They're eligible to be in the team. 4 physicists are there. My goal is to set up a team consisting of 1 mathematician and 1 physicist. In how many ways do you think I can do that? I mean, this is already clear for you, yes? Yes? Yeah. You raise your hand, yes?
I think it's like 4 factorial.
No. Don't make it hard. Yes. So let us think. It's not hard. I have 4 physicists, 5 mathematicians. So physicist. So I have physicist number 1, physicist number 2, physicist number 3, physicist number 4, with different names, of course, different people. And then I have mathematician 1, mathematician 2, mathematician 3, mathematician 4, mathematician 5. Okay? And I want to make a team, yes, to solve a problem. For this problem, I need a physicist be involved and a mathematician. Let us say that all of them are eligible, so I don't have any restrictions. In how many ways I can choose my team? Yes? 20, yes. Because I have 4 options for physicists, 5 options for mathematics. For example, one possibility is that I choose physicist number 1 with mathematician number 1. This is one possibility, yes? But another possibility is to do what? Physicist 1, I choose physicist 1, but this time I might be able to, I might choose mathematician number 2. This is one possibility for my team. That is another possibility for my team. Of course, the physicist is the same, but this team as a whole is distinct from that team as a whole, yes? We can recognize it. And of course, I can choose physicist number 1 up to with mathematician 3, and I can continue this list physicist number 1 and mathematician number 5. But that is not the only options that I have here. These are not the only ones. I can choose physicist number 2 with mathematician number 1, yes? So I have 5 options here. If my physicist is physicist number 1, I have 5 options here if my physicist is physicist number 2, and etc. So in total, it is clear that I have 20 options to set up my team in total. And that is the product principle. So you use the product. You take 4 and multiply it by 5. Okay? So already we know what is the product rule or the product principle, sorry. But I want to express it in more systematic way. I talk a lot for simple things, apparently, but please trust me. Try to train your brain thinking that way. Sooner or later, you will get confused between addition and multiplication. So this will happen. It happened for everyone. It will also happen for you. Okay. So try to understand them in a systematic way. So now, if I want to express the product principle systematically, I would say that let us say that I have a task to do. Okay, we want to accomplish a task. But this task can be broken into 2 stages, can be broken down into 2 stages. The stage number 1, stage number 2. Okay? And let us say that the stage number 1 can be done in n distinct ways. Okay? And now let us say that the stage number 1 is done in one of these n ways. After this is done, the second stage, independent of how the first stage is done, can be done in m different ways. Yes? Then, to accomplish the task, meaning that doing stage 1 and 2 one after the other, I have how many options? N times m options. Yes? Of course, I don't want you to digest what I told you immediately, but I want to express. So let us say that I have a task. What is my task here? You need to cook up some story. You just tell a story to yourself. Here my story is, my task is to set up a team consisting of 1 mathematician and 1 physicist. So this is the story for my task. This is the task, okay? But is it possible to decompose this task into 2 stages? Yes? Can I do that? Yes. So just tell a story for stage 1. What is a stage 1? Yeah, choose a physicist. This is the story that I tell for stage 1 to myself. And a stage 2 is another story. Choose a mathematician. Yes? So you see here, the task was to set up a team, but this task can be can be thought about going to two stages. Stage one, choosing a physicist. Stage two, choosing a mathematician. Okay. Okay, so that's the meaning of having a task that can be done in two stages. But now let us say a stage number one can be accomplished in n different ways. So a stage one was choosing a physicist. In my case, in how many ways I can do a stage one? Four. Because I have four physicists and I can choose any one of them, so I have four options. Okay? But when I go to a stage two, what was a stage two? Stage two was choosing a mathematician. In how many ways I can do a stage two? Five. But when you want to say five, you have to be careful. Is this five that I write for the second stage is independent of how the stage one is done? In other words, it might happen that in a stage one I choose physicist one. How many options will be left for me for a stage two? Five. But is this five independent of how I have done a stage one? Meaning that if I have chosen physicist number two, how many options are still available? Five. If I have chosen person three, physicist three, still five. So that is the meaning of independent of how the first stage is done. Okay? So I have a task. It can be broken down into two stages. The stage number one can be done in n distinct ways. After the first stage done in one of these n ways, a stage number two, independent of how stage one is done, can be done in m different ways. Then to accomplish my task, I have n times m distinct ways. Is that right? Yes or no? But I will give you examples to understand exactly what it means. Be careful. Again, let me repeat. This number should be independent. I'm not saying it is independent of stage one. I am saying this number is independent of how stage one is done. Yes? Okay. So for example, in this problem, you say that my task, I know that even myself will be lazy to write all those stories, but I will tell those stories to myself. So when I want to solve this problem, I would say that what is my task? My task is to set up a team. Is this possible? Is it possible to break it down into two stages? The answer is yes. I will repeat the stages in my head. Stage one is choosing a physicist. Stage two is choosing a mathematician. And then I will think that how many ways I can do this, how many ways I can do this. For this one, I don't need to be careful, but for this one, I have to be careful if this number is independent of how the stage one is done. Yes?
If you had to choose two physicists.
Now we come to those stories later, okay? But let us try to understand. Okay, for example, let me give you a very simple question. Here, of course, the answer was, do you agree that now this is exactly based on product principle? Yes? Setting up a team, stage one can be done in four different ways. After the first stage is done in one of these ways, stage number two, independent of how stage one is done, can be done in five ways. So it means that in total, I have 4 times 5, which is 20 methods, yes? But let me give you another example. So how many two-digit numbers are there? Yes, this is a very simple question, yes, example. How many two-digit numbers are there? Of course, this is an extremely easy question to answer. Before, even without knowing this, what is the answer? 90, yes? Because the first one is 10, next one is 11, 12, and then you go up to 99. From 10 to 80, from 10 to 99, still if you think there are 89, you're wrong, yes? Do you remember we had this before? From 10, including 10, up to 99, including 99, there is 99 minus 10 plus 1, which is 90. Yes, you are right. So there are 90 numbers there, which are two-digit numbers. But I want you to solve the problem using this product principle. Okay? So now you have to tell me stories, yes? So what is my story for my task here?
You have to first pick.
No, tell me the story of the task first. So what is my task here?
Make a two-digit number.
Yes, well, I will write down a two-digit number, if you don't mind, okay? So task, I don't want you to write this in the exam, but I want you to really think in this way, because this becomes a very serious problem for you if you don't get used to this way of thinking. So writing down, the first few examples, I will write them. Writing down a two-digit number. This is the story for the task. Okay, but is this task somehow can be broken into two distinct stages? Yes, because if I ask you to write a two-digit number, everyone can write this. For example, I write 82. But to be honest, if of course this task was so simple that I didn't think, but my brain processed. I just wrote something for the left digit. I just chose 2, and then write something for the right digit. I chose 2. But in principle, it was done so fast in my head that I even don't think about it. But this task can be broken into two parts. The first part is writing the left digit. The second part is writing the right digit. So let us write this story. So stage 1 is what? Writing down. Stage 1, let me write, picking the 10th digit. Yes? Yes, I have to write S here. Yes? And then S2, stage number 2, picking the units digit, yes? Yes? So this is a story that I tell to myself, okay? But let us go back and ask this question. So do you agree with me? This is my task. This task, even though this is very strange, but I can break it into two stages. Stage number 1, in how many ways I can do stage number 1? Yes, because I want to write a two-digit number. The digits available for me, as you know, are these numbers, yes? Yes? These are my numbers. So for this one, how many choices I have? Because I insist to have a two-digit number, so then you have some limitations. So you cannot put 0 on the left. Because if you write 0, 2, in principle, in mathematics, this is not called a two-digit number. It is just simply 2, and 2 is one-digit number. So I have some limitations. So how many ways I have available?
1, 2, 3, 4, 5, 6.
Yes, so which is, I can choose one of these, and then if I count them, how many of them are there? None. So the number of ways that I can accomplish stage 1 is 9. Yes? This is so simple, but be patient. This becomes very hard. So, and then n becomes 9. Now, if you want to go to the second stage, you want to know how many ways I can do stage number 2. When you come here, you need to think in this way. Assume that a stage 1 is done. What does it mean? It means that you picked one of them and put on the 10th digit, yes? This is done. Now how many ways I can do this one? How many choices I have for this digit? 10. Because this time I can use 0 as well. But when you want to write 10, this time you have to be careful. You don't need to be very careful. But when you want to write 10 here, you have to be careful. How? You need to know that is this 10 independent of how stage 1 is done? In other words, let us say in a stage 1, I choose 1. Okay? Now I go to a stage 2. How many options are available in front of me? 10. Let us say, no, I didn't choose 1 here, I chose 4 here. But for stage 2, again, how many options are available in front of me? 10. So you have to convince yourself, you don't need to explain and write things in the exam, but you have to convince yourself that this number that you put here is independent of how this is done already. Okay? If this is the case, it means the product principle is applicable, and the answer to the question is extremely simple. 9 times 10, which is 19. And that is exactly the answer that you expected. Yes, is that clear? Okay. So let me give you an example to understand this a little bit better. Okay, so let us say that I have two cities, city X, I call it city X, and city Y, and let us say that I have 5 roads connecting them. Okay, and all of them are two-way roads. I can go back and forth between them in any one of them. So let us say my goal is this. I want to start from city X, go to city Y, spend some while, and then come back again. But because I want to enjoy the landscape or whatever story you can tell to yourself, I do not want to choose the same road that I use for going. I want to go from one road and return back through another road. Okay, so let us see in how many ways I can do this project. It's extremely simple. Don't just the answer. I want you to cook up the stories. Okay, so what is the task here? The task is exactly as I told you, yes? Go from X to Y and return. Don't use the same road. Now, I'm just writing it because I just told you orally, okay? So go from X to Y and return. Don't use the same road. You understand what I mean, yes?
Yes.
Yes. But is this task, this is my task, okay? Is it possible to break this down into 2 stages? Yes. So stage number 1, what can I tell to myself?
Choose a road.
Yeah, picking a road from what?
X to Y.
X to Y. And then S2, picking a road from Y to X. Yes, is that right? Okay, and if you don't mind, let me give them names. Road A, B, C, D, E. Okay, be careful. When this task is accomplished, this is very important because later we will have the sum rule or the sum principle. When this task is accomplished, if I do a stage 1 and forget about stage 2, my task is not finished. Yes, exactly like here. This number, this 2-digit number, the task is written down if I have chosen the left and the right digits. If I choose the left digit and forget about the second stage, my task is not done. So be careful. This is one of the main features of the product principle. The task is accomplished if and only if all the stages, one after the other, are done. Otherwise, the task is not finished yet. Okay, so the same story here. Okay, how many options I have for S1? That's extremely easy task. Yes, what's that? So n is 5. Okay, but now think in that way. Let us say stage 1 is done. What is the meaning of this sentence? It means that let us assume that one of these roads is picked for going from X to Y. Whatever. Okay. How many options I have from Y to X based on the task that I defined to myself? 4. Yes. Be careful about this one only. When you want to write number here, you told me 4. But be careful. Is this 4 needs information from stage 1? In other words, is this 4 independent of which road I have chose for this?
Yes.
The number is independent, but the stage 2 depends on a stage 1. The number of ways that I can do a stage 2 is independent from stage 1. Yes, this is important. So let me tell you how. Let me draw a diagram. So for going, I have how many options in front of me? Let us draw a tree diagram. Yes, I can choose one. So stage 1, I can choose road A to go from X to Y. Yes, so I am in here X, and okay, I don't want to write so much things, but this is, I can choose A to go, B to go, C to go, D and E to go. Yes. If I choose A to go, and I want to come back, and I want to respect my condition, how many options I have? I have 4. But what are my options? B, C, D, E, because my constraint is that don't use the same road. Here I have used road A. When I want to come back, I have these choices. Yes? How many of them are there? 4. But now let us say that I have chosen this one. How many options I have again? I have 4, but the options are different. So what happens here? I have A, C, D, and E. I am not telling you, be careful. You see, the way that I can do the second stage is not independent from the first stage. It affects, if I choose A, these are my options. If I choose B, these are my options, which are different from the previous options. But the important thing is that the number of options is still 4. Yes? And then again, I go here. What are my choices? I have 4 choices, different, of course. So it is A, B, D, and E. Here I have again 4 options. What? A, B, C, E. And here I have A, B, C, D. So you see, I am not telling you accomplishing a stage 2 is completely independent from how stage 1 is done. No, it depends. If you choose A, these are your options. If you choose B, these are your options. The options are different, but the important thing is that the number of options is the same. 4, 4, 4, 4, 4. Okay? So this means that is the product rule, product principle applicable? Yes, everything is okay. So the answer to the question mark is just simply 5 times 4, which is 20. Okay? And still, to understand this a little bit better, let me modify the problem a little bit differently. So now let us go back to the same situation. My task is still the same, but let us assume that 2 of these roads are one-way road. Okay? So, for example, A and B are one-way road from X to Y, so you cannot choose them to return. Okay, and I want to do the same problem. Let us see how it will modify itself. Is the question clear? Okay. So the task is still the same. The stages are also the same. So what is this number, do you think now? It's still 5. I have 5 options available in front of me to choose my road from X to Y. Yes? So still that's 5. But about 4. Let us go see that how many options are available for me for the second stage. Okay? I don't want you to solve it, but I want you to feel, is the product principle applicable or not? So, can I simply write 4? Do you see? I want you to feel that. If you want to write 4, you cannot write confidently 4, because you would say it depends which road I have chosen. Do you see that? Why? Because if I have chosen A in the first stage, because when you say 5, A is one of my options. If I have chosen A, when I want to come back, how many options are available in front of me? 3. So let us write 3. Okay? If I have chosen B to go from X to Y, how many options are available for me to return? 3 again. So that's good. But it doesn't go like that, yes? Because if I have chosen C from X to Y, when I want to go back, what should I do? I cannot use this, I cannot use that, and because of my constraint, I don't use C myself. So how many options will be available? 2. So you cannot confidently write 3. This 3 is sometimes 3, sometimes 2, depending on how you have done the first stage. Is that clear?
Yes.
So this means that the product rule is not applicable. Of course, it doesn't mean this is a hard problem to solve. It's an extremely simple problem to solve, and we'll learn. But it needs something else. It needs consider 2 scenarios, yes? And then add them up. That would be another principle, which is the sum principle. We will come to that, but don't get confused right now. I am not asking you to solve the problem. I want you to understand that this is a little bit different from the previous scenario. Here, you cannot confidently write 3. You cannot confidently write 2. You need to know how this stage is done. If you need to know how the previous stage is done in order to be able to write something, it means the product principle is not applicable, directly at least. Yes? So for example, if I want to draw the same diagram, this is the tree diagram, for this new scenario, again, the first stage does not change. I have A, B, C, D, E still. But now, what happens here? If I have chosen A to go, how many options are available for me to come back? 3 options. What are they? C, D, E. Yes? And if I have chosen B, how many options are available?
3.
Again, C, D, and E. But if I have chosen C, how many options are available?
2.
2. What are they?
D and E.
D and E. And if I have chosen this, how many options are available? 2. And how many of them are there?
2.
So what are they?
C and E.
C and E, and here C and D. Do you agree?
Yes.
So you see, in some branch I have 3 coming out. In some of these branches I have 2 coming out. So it is not evenly written. You see, sometimes 3, sometimes 2. But here in this case, it was always 4. Yes? So of course you can answer this yes, because you have 2 branches. And from these 2 branches, I have 3 branches coming out. So 2 times 3 is 6. And then I have 3 branches, 2 coming out. So 3 times 2 is again 6. So in total, I have 12 ways to do that. But I am adding them. So that is not just multiplying them. Yes, for example, here, one way is A and C. What is the meaning of this? It means that I choose road A to go and choose road C to come back. This is the meaning of this. So how many of these pairs you can write from this diagram? Yes, AC, AD, AE, BC, BD, BE, CD, CE, DC, DE, EC, ED. And if you want to answer, count them, it is not hard, yes? You can write them down and count them one by one, or you can be wiser. You can see that I have 3 times 3, sorry, 2 times 3, or plus 3 times 2. Yes? But what I want you to understand is that the product principle is not alone enough to solve this problem. Is that clear?
Yes.
So that is the meaning. So I want you to digest that. And I know that it doesn't matter how many times I repeat this, you will not care about what I'm saying, most of you. But try to understand this. In the beginning, I'm not expecting you to write this down, but still, when I want to solve this problem, I tell these stories in my head. And then follow them, okay? Otherwise, it becomes hard. Okay. Let me ask you another question. Right in the beginning, I want to draw your attention to one very important point here. So here, the task was writing a 2-digit number. Because we write from left to right, this stage, this way of breaking the task was a natural order. It was in natural order, yes? If you want to write 82, you write 8 first and then 2 seconds. But for product principle, it doesn't matter. Okay? So let us try to solve this problem to see if it works or not. This is a very important thing I want you to learn. So let me define my task as it is here. I want to write a 2-digit number. But let me take a stage 1, strangely picking the units digit. Okay? So it is not a natural order, but let me write S1 picking the 10th, the units digit. Yes? And S2 picking the 10th digit, yes? Agree? Okay, but let me ask you again. So in how many ways I can do that? I'm telling you, this order is not the natural order. But the principle, product principle doesn't care about what you call natural. Yes? So let us see if it works or not. So the first step is to pick the units digit. In how many ways I can choose the units digit? 10. Because I don't have any limitations. Even I can put 0 in the units digit. So this becomes 10. And in how many ways I can choose the 10th digit?
9.
9. When you want to write 9, you have to be careful. Is this 9 independent of how this one is done? Yes. Regardless of what you have chosen for your units digit, for the 10th digit, you have 9 options. Yes? So, is the product rule applicable? Yes. So, the answer to the question mark is 10 times 9, which is, of course, again, 90. So, it works. Of course, the reason that I'm talking about this, because sometimes the natural order is not a good order if you want to write the use the product principle. By interchanging the natural order, you can still solve the problem using the product principle. I give you examples. Okay, let me wait a little bit here too, so that you can digest. The problem is not hard at all, yes? So I have one task. The nature of this task is in a way that I can imagine I can break it down into two parts. And then I know in how many ways part one can be done. And after the part one is done, I also know in how many ways part two can be done. But the only thing that you have to be careful is the second number should be independent of how part one is done. Yes, that's the only thing that you have to imagine. And if everything is okay, you just multiply them. And the number that you get is the total number of ways that your task can be done. And it means that, so here, I want you to understand, this is a very important feature. The task is not accomplished unless both of them are done. If you do one of them and leave, the task is not finished. Yes? Is that clear? So, okay, let us try to practice a little bit about these concepts. Okay, now that you learned storytelling, I'm also lazy, so we try to summarize this. Let me go and ask this question. How many odd two-digit number are there? Or let me make it very simple. How many two-digit numbers are there with distinct digits? Yes, for example, 11 is a two-digit number, but that is not what I want now, because 1, they are not distinct. Okay, so you can immediately answer. In total, how many two-digit numbers are there? 90. And then, of course, you say that 11 is not acceptable. What is not acceptable? 22 is not acceptable. 33 is not acceptable. So how many unacceptable ones you have? 9. 11, 22, up to 99. So that is 9. Do you agree? So 11, 22, 33, 44, 55, 66, 77, what is that? 88, 99, am I right? 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 of them is not acceptable. Yes, so you can immediately answer. So what is that? 90 was the total number of them. I had 90, where was it? I had 92 digit numbers without any constraints. But this time, I am, for some reason, interested in two-digit numbers with distinct digits. If I ask you how many of them are there, this is one way to look at it, yes? These are not acceptable, I throw them away. So how many of them are left? 81. But that is not what I want you to do. Okay, I want you to solve the problem using the product principle because I want you to train your brain to get used to this way of thinking. Okay, so what is your task here? So the problem's clear? Okay, so what is the task here? The task here is to write a two-digit number with distinct digits. I just told you. I told this story to myself. And then let us write this one. For numbers, it is good to have this one. I can accomplish it in two stages. Writing this digit and writing that digit. For the time being, let us keep the natural order. So let me call it a stage 1. And let me call this one a stage 2. Yes? A stage 1 is picking this number. In how many ways I can pick this number?
9.
Why 9? Because I have 0, 1, 2, up to 9, 10. 0 is not allowed for this. So how many is left? 9. So I put 9 here. Be careful. Okay, now, so this is usually easy. Stage 1 doesn't poses any problems, yes? Because it's very simple. But for stage 2, you have to be careful. When you want to put something here, you count them, but you have to be careful what you put here is independent of how this is done. Okay, so now let me write the digits. It is good to write it in front of your eyes for the first few examples. 1, 2, 3, 4, 5, 6, 7, 8, 9. I know that this is filled now. I know 0 is not here, but I don't know which one is there. This is filled with one of the possible options. Yes? this is done. How many options are there?
9.
Why 9? Because I am not allowed to repeat a digit. Yes? I know that one of these digits is used here. For the second one, I am not allowed to use that. For example, assume that 1 is done. 1 is chosen here. So it means that I have to take this from my list because I'm not allowed to choose it again. But can I choose 0 for this one? So how many options are available? 1, 2, 3, 4, 5, 6, 7, 8, 9. You want to write 9, but be careful. Is this 9 independent of how the first one is done? Let us assume that 1 is not chosen here. Let us assume that 3 is chosen here. For the second stage, I am not allowed to choose 3 because the digits should be distinct. But how many options are again available? 9. So you see, this 9 is independent of how the first stage is done. Of course, in principle, you have to think about all possibilities. 1 is dropped, this remains 9. 2 is dropped, this remains 9, and up to the end. Okay, so I hope that now you understand this 9 is independent of that option. So how many are, so is the product rule, product principle applicable?
Yes.
Yes. So the answer is 9 times 9, which is 81, as we predicted. Is that clear? Okay, so let me ask you this question. How many odd two-digit numbers are there? Okay, you already know the answer. How many odd two-digit numbers are there? 45. Because what was the total number? 90. Half of them are odd, half of them are even. So you already know the answer. But I want you to do it using the product principle to learn that. Okay, so the question is that how many odd two-digit numbers are there? Okay, so the task is writing down a two-digit odd number. Stage 1 is still good, picking the 10th digit. Stage 2 is picking the unit digit, the same as before. So I can write it like this: stage 1, stage 2. Yes? Okay, how many ways? Let me write them down again. These are my digits. I want to fill up stage 1. How many options are available? 9, because the only problem is 0. So I have 9 options available. Now my goal is to write an odd two-digit number. So what does it mean? It means that I have a lot of constraints for S2. So which numbers are allowed to be chosen for the units digit if I want to have my number odd?
Only odd numbers.
So this one is possible for that one. This one is possible, this one is possible, this one is possible, this one is possible. So how many of them are there? 5. But be careful. When you want to write 5, you need to understand, is it possible to write 5 independent of my choice in the first one? Do you think that this 5 is independent of what I have chosen in the first stage?
Yes.
Yes or no?
Yes.
Yes. Because, for example, let us say that I have chosen number 1 for stage 1. But how many options are available for stage 2? Again, only these numbers. So that's clear. So this is important to understand. This number that you put here needs attention. This one usually doesn't need attention. It's very easy. But the second one needs attention. Okay, so you need to convince yourself about that this number is independent how it's done, and if it is the case, the answer, be sure that the answer is this, and which in this case is correct. Yes? Now let me do another question. How many odd two-digit numbers with distinct digits are there? Yes? So you see that the problems are extremely simple. Yes? So we want to answer this question. I want to have a two-digit number. I want to be odd, and I want to have distinct digits. Okay? Let us try to see how it works. So tell me again. The first things come to mind is this task also can be broken into 2 stages, and let us take the natural order. Natural order in this case is S1 and S2. Yes, let us see if it works or not. So in how many ways I can fill up S1? 9, yes? Yes? And how many, so now assume that S1 is done. What is the meaning? It means that I picked one of these numbers and put it there. Okay? Now I want to go to S2. In how many ways I can fill up S2?
Either 5 or 4.
Yes, you see, you have to say either this or that. Do you feel that? Because, for example, let us say that I have chosen 2 for stage 1. Yes? When I go to a stage 2, because I want to keep it odd, and so I don't have any problems. I choose these ones, yes? So it becomes 5. Yes? But this is not the whole story. Do you agree that this 5 is not for all cases? Because it might happen when you write 9, one of your choices is to pick up 1. Yes? But because this time the digits should be distinct, you are not allowed to choose 1 again for the units digit. But still, you insist to keep it odd. So how many options will be available?
4.
4. So you cannot say 5 for sure. You cannot say 4 for sure. So you have to write 4. This means that we cannot solve this in one step in this way, using the product principle. Is that clear? Understandable? Okay. Now let us switch the order. Okay, I want to switch the order from natural order to some artificial order because we don't write numbers from right to left. But as far as principle concerns, it doesn't care. If it works, it doesn't care. Okay, let us try to understand this one. So this time, it doesn't mean we cannot solve it in this way. What I'm telling you, you cannot just simply write 9.5 or 9.4. Yes, this is not possible. But now let us say that I interchange the role of stages to a strange one, yes? Put a stage 1 here and a stage 2 there. Okay? Now I ask you the same question. You want to choose this number. Okay? Be careful. You want to have 2 digits, odd, distinct digits. But stage 1 doesn't care about any of them. You just want to care about being odd. So how many options I have here? 5. Okay? But now, assume that stage 1 is done. What is the meaning of this sentence? It means that one of these 5 options is now chosen and fixed in position 1. Okay? And how many options are available for us too? 8. Yes? I want you to know that. Is this 8 for certain? Or you have to say this or that? Because let us try to understand. When you say 5 is available for S1, one of your options is to put 1 there. Do you agree? Okay. When you come to this number, am I allowed to choose 1 again? No, because I want to respect being distinct. But I also not 0 is not also available there. So 2 of them are gone. How many of them are left? 8. But you don't be in a hurry. You have to make sure that this 8 remains the same for all choices of stage 1. Let us say that I didn't choose 1. Let us say I chose this odd number. And then I want to go to a stage 2. Because of respecting this condition, 3 cannot be chosen anymore. 0 cannot be chosen because I know 0 cannot be in the 10th digit. And then how many options are available? 8 again. Do you agree that this 8 is confident? We are confident about 8 here. Yes or no? Yes. And then, so is the product principle applicable? Yes. And the answer is? 40. So that's a very good example to see that sometimes the natural order is not the best order to solve this problem, but if I interchange the order, the problem is solved. And I hope that you can confirm this answer is correct. Can you confirm that? How many odd numbers we had? 45. But this time I do not want to have the digits repeated. Okay? Odd numbers, 45. How many of them I have to eliminate? 11 is not acceptable because it is odd, but the digits are repeated. 33 is not possible. 55 is not possible. So how many of them I have to take off? 5. How many odd numbers I had? 45. 5 of them are gone, 40. So 40 is really correct. Yes? Is that clear? Yes or no?
Yes.
Okay. So this is a very important lesson to see. In these problems, I myself always start with the natural order. But before jumping to a harder way of solving the problem, if it doesn't work, I try to see that changing the order works. And my experience, this is the rule of thumb, is that by experience, if I want to start the problem, I know that I have to start from S1 because I have more constraints for S1. This is my observation. I mean, this is not a mathematical rigorous proof. But whenever you want to write stages, my preference is to start with the stages with more limitation. Yes? So here I have more limitations than this one. Yes, here I have only 5 choices because I want to have. This is my experience. It's better to start with the one that you have more limitations. Okay, is that clear? So all of these that are very important but very simple ones, I want you to start respecting them because their problems becomes immediately hard. And then I am sure that you get confused. You get confused between adding and multiplying. Yes, try to understand. Okay, now of course this problem is boring if I just want to talk about a task which can be done in 2 stages. We want to always, if you're a mathematician, when you solve your problem, you cannot sleep, you make a problem, then you work on the morning. Okay, the problem that you want, what's your natural question now? If you're a mathematician, what do you do? Yes?
If that's 3 stages?
3 stages. If I have a task that cannot be done in 2 stages, but can be done in 3 stages, but can you formulate it for me now? Yourself. I want you to rely on your intuition. Okay, yes.
Maybe you add the hundreds digits.
No. I want to talk about product principle, but this was for a task that can be done in 2 stages. But as you mentioned an example, if I want to write a 3-digit number, this can be done in 3 stages. So I need a version of product principle which is suitable for your question. And then, of course, I can write a 4-digit or thousands of other examples, yes? So I want you to formulate for me the product principle for a task that can be accomplished in 3 stages, but carefully. I start, okay? I will start with this. Let us assume that I have a task that can be broken down into 3 stages. Okay, now you tell me. If a stage 1 can be done, let us say in 1 ways, okay? And then?
Stage 2 can be done in 2 ways.
No, be careful. I want to tell me everything. That is the very summarized version, okay? If after S1 is done in one of these ways, a stage number 2, no? Independent of how stage 1 is done, can be done in n sub 2 ways, and
when stage 1 and stage 2 are done,
yes,
stage 3 can be done in 3 ways independent of how stage 1 and stage
2 are done. Yes, so you see this is the case. A stage 1. So let us repeat. A stage 1 can be done in n1 ways. A stage 2, after stage 1 is done, independent of how it is done, can be done in two ways. And a stage 3, after stage 1 and stage 2 are done, and independent of how they are done, this can be done in n3 ways. Then in total, the task can be done in how many ways? In the multiplication of them. Yes? And then you can continue this for a task with 4 stages, 5 stages. The important thing is that when I continue these stages, every stage, when I write a number, this number should be independent of how the previous stages are done. So it seems become hard, but of course this is the way. It doesn't become that much hard, but I told you, the nature of these problems are extremely hard. Yes? I mean, you read the problem, and then you actually lose whatever you know about multiplication and addition, yes? Because you get immediately confused, and that is the fun part. Okay, now let us try to understand. For 2-digit number, we didn't discover that much because we could solve the problem much easily. Yes? But let me ask the same questions for three-digit number. Then you immediately realize it is not easy to answer. For example, if I tell you how many three-digit numbers are there, this you can solve without this nonsense, okay? So how can you say how many three-digit numbers are there? The first three-digit number is 100. The last one is 999. So how many three-digit numbers are there? What?
899.
No, don't tell me. Believe me, 999, no, 899, the difference, but plus 1. 900, huh? What you said is correct. Yes. Yes? So how many three-digit numbers are there? 900. Okay? But let us use this three-stage task. Yes? Because if I want to write a three-digit number, this task can be broken down in how many pieces, in how many stages? 3 stages. Yes? So let me write now this. Let us take the natural order. Stage number 1, writing the 100th digit. Stage number 2, writing the middle digit. And stage number 3, writing the... This is the natural order. Okay. How many options I have for stage 1?
9.
Because the only constraint is I am not allowed to put 0. Except that I can put all of them. Okay? But now when I go to the middle one, how many choices I have? 10. Because 0 can also be here. Okay? And then, is this 10 independent of how this is done? Yes, it doesn't matter. So now I go to a stage 3. In how many ways I can fill up this? 10 again. But be careful. Is this 10 independent of this and that? I really don't need to know what numbers are chosen here. Whatever they are chosen here, I have how many options? 10. So is the modified version of the product principle applicable? Yes. So you just multiply them. 9 times 10 times 10 is how much?
900.
And that is according to your prediction. And still it is not fascinating because you could come up with 900 in a different way. But let me ask you the same question. How many three-digit numbers are there with distinct digits? Then you immediately realize that is not easy to answer right away. Of course, you can start writing all of them and then cross them over, or you can write a code. Okay? But I want you to say that, how do you answer that? Let us say that you don't know the product principle. You want to only consider three-digit numbers that digits are all distinct. For example, 1114 is not acceptable. Yes? Because 1 is repeated. I don't know, 555 is not acceptable. Yes? So you want to consider only three-digit numbers that the digits are all distinct. I want you to feel that we are doing something here. Yes? This is not just we're solving trivial problems. Do you feel that? Okay, now we'll answer this question. So, is the question clear? I want to write a three-digit number. This is killing me. Okay, so stage 1, stage 2, stage 2. Let us keep the natural order for the time being. But be careful. The task is writing a three-digit number, but I want to have the digits distinct. So how many options available for S1? None. Because the only thing that I cannot put there is 0. Think in this way. This is done in one of the ways. Now how many options are available here? 9. Do you see that? Because here I couldn't put 0. For this one, so when I cannot put 0, it means I put one of them there, one of these 9 ones. I put one of them there, but because I want to respect to be distinct, in the second one, I can choose 0, but I cannot choose the one that I chose here. Is that right?
Yes.
So how many options are available? 9. Okay? Okay. And I hope that you agree, this 9 is independent of how this is done. And then here, how many options are available?
8.
Do you agree with me?
Yes.
Because here, I cannot choose the previous ones, but I can choose 0 if I want to. Is this 8 here independent of how these two are done? Is that understandable? It's not by the way, it's not mathematics, it is just a primary school task. might be you are confused, but you can sit down and then write them and cross them over. Yes, is that clear? This is 8.
Yes.
Yes or no?
Yes.
Okay, so you multiply them. So 998, so it's 648. And by the way, 648 was not an answer that you come up with immediately. So today we did something. Yes, we counted this without writing them and counting them. And it was a non-trivial problem. The previous ones were trivial, but I want you to learn how to use this for the product principle. But probably this is the first problem that you solve, which is not trivial. So there are 648 three-digit numbers in which the digits are all distinct. Yes? Okay, let us make the problem interesting. Let us ask the questions. Okay, again, how many three-digit numbers are there? How many three-digit numbers are there that are odd? Okay, so let us answer this. You already know the answer from a different way. What is that?
450.
Not here. I'm talking about all digit numbers, all three-digit numbers. Yes. How? By the way, don't be confused. I ask you how many odd three-digit numbers are there. I didn't say anything about being distinct. Yes. So you shouldn't push this. Okay. So forget about this. How many three-digit and odd numbers are there?
450.
Yes. Based on your intuition, it should be half of this number. This was the total number of three-digit numbers. You divide by 2, 450. But I want you to solve it using the product principle to learn. Okay? By the way, in the exam, you don't have to. If you find an alternative way that you can understand better, you can always use. But I promise you, I give you questions that you cannot do that. Okay? So try to learn product principle. Okay, so what can I do? I want this time, let us keep the natural order. Or do you want me to do that? Okay, so let me just do that. Okay, so I want to have an odd number here. So how many options are available here? If I take this stage 1, stage 2, stage 3, let us see if it works or not. How many options are available here? None. Let us say this is done in one way. How many options are available here? 10. Yes? Because I can choose anything. But how many options are available here? 5. Independent of how they are done. Yes, because I want to have odd. Did it work? Do you agree with me that this is independent from here and this is independent from these two? If this is the case and you are convinced and you are not wrong, don't doubt. The answer is what? 90 times 5, as you predicted, was correct. Yes? Okay. Now, let us solve your question. This time I want to have odd 3-digit with distinct digits. Okay? So let us now keep the same natural order to see if I have problems. Based on your experience, and as a rule of thumb I told you, you might think that you will face a problem. So I will not start from the natural order because I have experience. But you have to do it to see why it doesn't work, change it, and then learn. Okay? But let us try to, let me put myself in your shoes. Okay? So if I want to do this, how many options are available for S1? So you know the problem. 3-digit, odd, distinct. So what should I write for S1? 9. How many options are available here? Be careful. This time I don't want to use the same digit here as I've used here.
9.
8 or 9?
9.
9 again. Because this time I cannot use this, but I don't have any constraints about 0. Here when I said 9, I eliminated 0 of putting here. So for example, I put 7 here. And then I am not allowed to put 7 here because I want to respect to be distinct, but I can use 0. So still, one option is gone, but one thing is there. So I have 9 options. Yes? But when I go to the next one, can I be certain about the number that I can put here? Do you see that? The answer is no. It depends to a lot of things. For example, one possibility is that I have chosen 1 here, and 3 here, and I want to keep this odd. So how many options are available? And I don't want to repeat a digit. 1 and 3 are gone. For this one, in principle, 5 options are available. 1, 3, 5, 7, and 9. 2 of them are used. How many of them are left? 3. So if I use this and this, then I have to write 3 here. But it might happen that I use this for here, this one for here. How many options are left for here?
4.
4. Or 4. Or it might happen that I use 2 here, 4 here. How many options are available there? 5. So these ORs are problematic. If you come up with OR, it means the product principle is violated. Is that clear?
Yes.
But it doesn't mean that get disappointed. Might be we have another trick in our tool, yes? Toolbox. What is that? Yes?
You put the units digit as stage 1.
Yes, by that experience. But sometimes it even doesn't work. But it is better than nothing. Yes? Let us change the order. So this doesn't work. Just cross it over. And then which one you prefer? Which one do you want to take as stage 1? As a rule of thumb, the one which you have more constraints. So what is that one?
Stage 3.
Yeah, that one, the right one. Stage 1. Which one you prefer to call stage 2?
Second, middle
No, I will prefer the last one. Because for the middle one, I do not have any constraints. But for this one, 0 cannot be there. Yes? Here, I have 1 constraint, 0 cannot be there. Here, I have 5 constraints, or even numbers cannot be there. So I prefer to jump from here to here. Yes? And then write this one, number 3. Yes? This is the way that I have constraints. I'm not saying it will work, but it might work. Yes? Okay, S1. How many options you have for S1?
5.
5. Odd numbers. So I put 5 here. Whatever I put here is not available for here because I want to respect to have distinct digits. So how many options are available for S2? 8. Why? Because 0 is not allowed. The one that I used here is not allowed either. So how many of them are left? 8. Be careful. Is this 8 independent of which one I have chosen there? I could have chosen 1, still I have 8. I could have chosen 3, still I have 8. I could have chosen 5, still I have 8, etc. So this 8 is independent of how this is done. Now these 2 are done. I go to the next stage. What can I write there? 8. Yes? Because two numbers are chosen there. I am not allowed to use them there. So it means that 8 options are available that I can use. But before putting 8 here, you have to convince yourself this 8 is independent of how this and this are done. Is it independent?
Yes.
Do you agree?
Yes.
So this solved my problem. Yes? 5 times 8, 40 times that, 320. And I hope that you agree this is not an easy answer to come up with if you don't do it systematically. Okay? Is that clear?
Yes.
Okay. Now, let us try to solve this problem for even numbers. Okay? For even numbers. The same problem. Even 3-digit, even distinct digits. Okay? Now you have a little bit of experience. You don't start with natural order. You know that this is a dead end. Yes? So you start from an order like this. Do you agree with me?
Yes.
Are you with me or not?
Yes.
Yes. You know, you have to enjoy. If you don't enjoy, then you get bored, you know? Okay. Anyway, by the way, this is a real problem. Yes? Because when you want to design a system, by the way, you don't need to be a mathematician. Yes? If you are in a tax office or whatever. By the way, how many personal numbers we can have in Sweden? So probably you should be able to solve that. And then it becomes a catastrophic problem if the number of populations go really beyond the numbers that we can assign to people. So here we have the birth date and then we have 4 digits. You need to know the population of Sweden is around 10 million. So is this system of numbering enough or no? That is a very big problem, not just, in pure mathematics, in a practical problem, yes? But that's a good question to ask yourself, how many in this way that we have personal number here in Sweden, how many people can have different personal numbers. Anyway, so I'm waiting for you. 3-digit with distinct digits, even. So based on your experience, which one you prefer as S1?
The right.
The right one. Which one you prefer for S2?
Left.
The left one. And then probably this is probably a good experience. But let us see if it works this time or not. How many options are available for S1? 5. Which are they? 0, 2, 4, 6, and 8. 5, yes? Okay, now let us say that this is done. Now I jump to stage 2. Stage 2, how many options are there?
8.
8. If I write 8. But before writing 8, you have to be sure, is it independent of how this is done? Yes or no?
Yes.
Yes or no?
Yes.
If you know me, you should say no. It's whenever I say yes or no, I'm trying to pay your attention that it is no. Yes? Yes?
Is it 9?
It is 8 or 9.
8.
And it means that that is the dead end. So even if I change the order, why is that? Let us explain. When you write 5 here, what are your options here? 0, 2, 4, 6, 8. Yes? One possibility is to put 0 here. Okay? When you put 0 there, because you don't want to repeat the digit, you are not allowed to use 0. So you're using 1 up to 9. So you write how many times? How many things? 9. But another option is 2. It might happen that I put 2 there. Yes? In here, I am not allowed to choose 2 because I don't want to repeat. But I cannot choose 0 either. Yes? So 2 options are gone. So this is not 9 anymore. Is what?
8.
8. So you say or. When you say or, it means it is not independent. It means that one step, this problem cannot be solved in one step using just one single product rule. It doesn't mean that I can I cannot solve it. It's extremely simple. And I think you can also solve it yourself. I want to test your intuition, how you solve the problem.
Can we switch the stage 2 and stage 3?
It doesn't work. You can do that. Yes? But how can you solve it? No, you cannot solve it using product principle. But because this is a very trivial thing, I think you can do it. Yes?
Subtract all the cases where
Subtraction not at this stage. So I mean, what you are saying is true, but how can I count the other undesired ones? Yes? What you said is completely correct. We will come back to it. That's called complement rule. And it works. Yes? But let us say that one natural way is to say that, okay, let me count the even ones which 0 is not there. Yes? Count them. And then let us assume that this time 0 is there. And when I found the total number, add them. So the even numbers that I have are ending with 0 or not 0. Yes? So I can count this one and count that one and add them. But I don't want to confuse you because I will teach you later. But I want you to understand, I wanted to use the same trick. It didn't work for even case. Yes? Anyway. So the answer to this question is left when we learn the sum rule. Yes? Is that clear? Okay. Okay. Let us see. Okay, let me ask you this question. This is also based on my experience. Let us say that I have a room, so the aula, I don't know, for example, and the seats are labeled, number 1, number 2, number 3, etc. Okay? I have 30, this is too much here, we cannot, so I have 30 seats, chairs, with labels 1, 2, 3, up to 30. And then I have 5 students. Okay, so let me call them student A, B, C, D, E. In how many ways I can make them sit in this room. For example, one possibility is to say that this one sits number 1, 2, 3, 4, 5, and the left of the room is empty. One possibility, I say that I don't like you, you go to chair 30, I don't want to see your face, and then this is the problem, and then I like them, so they are close to me, I hate him, he goes back there, and this is one. And the important thing is that this one is different from the previous one. Everyone, by looking at this previous situation and the new situation, realize that something new happens. Yes? My question is that how many ways I can arrange them? I don't want to give you the final answer because the answer is very big, but I want you to write something in a product way. Yes?
Is it 30 times 29 times 28 times 27 times 26?
Yes. So that's the answer. This is why, you see, the problem immediately becomes complicated if you don't tell the story. That's why I'm emphasizing tell the story to yourself. Okay? So let us imagine that I really want to do it. What is my task? You need to define a task. Don't underestimate this. You have to define a task. What is my task here? Just say fiction, something, whatever.
Write down a seating arrangement for
Yes. Call them and let them sit in the places that I want. Something like that. This is my task. This task can be accomplished in how many stages? This is the way that you have to think. You see, the problem immediately becomes hard if you don't think in that way. Okay? So, this task that I want to let them sit can be accomplished in how many stages? 5. Yes? I say that A, go and sit there. B, go and sit there. This is a stage 2. This go sit there, the stage 3, and up to a stage 5. So you see, I am making a story for myself. This is important, by the way. Yes? So, and then I ask myself, how many ways I can do stage 1? It means I want to assign a chair to a student A. In how many ways I can do that? 30. Now assume that stage 1 is done. What is the meaning? It means a student A got a chair and now is located there. Now I go to the second stage of the task. What is the second stage of the task? Locate a chair for student B. Okay? How many options are available for me?
29.
Because this one of them is already occupied by first person. How many options are available for the second one? 29. Is this 29 independent of which chair is assigned to A? Yes, it doesn't matter which chair is assigned to A. The number of chairs available for the second person is 29. And hopefully you agree with me how many options are available for stage 3? 28, and then 20. And this 28 is independent of these two. 27 is independent of these two. And finally, 26 is independent of all of them. So the generalized product principle is applicable. So the answer is this big number. Multiplication of all of them. Is that right? So by giving you this example, I want you to see how important is that to tell a story exactly into the setup that I told you. Yes? When the time is finished, you know?
50.
Okay, so we have a little bit of time. Now, I changed the question, and I want to see how many of you answered that. This time, I have 30 students outside, only 5 chairs available. Of course, it is clear that it's not possible to let them sit all of them. I have to choose them. Yes? This problem, I have 5 chairs in the room, 30 students outside. In how many ways I can choose 5 of them and let them sit? I want you to think about it. For example, in this situation, I can choose you and let them sit, and then or I can choose the other group and let them sit. So this situation is different from that situation. In how many ways I can do this? Choose 5 students and let them sit. Not only I choose different combinations of students, but even if I have the same combination, I can rearrange you. That's also, you have to consider all possibilities. Not only the combination of people I choose, in the arrangement that I do. Yes? The situation that you are here and Parham is here is different from the situation that Samir is here and Parham is there. I want to consider all possibilities. So in how many ways I can do that?
30 times 29, 20.
Yes. So it means that you are not very selfish, because you know humans think that they are center of the world for some strange reason. Yes. Mathematics doesn't care about you. Mathematics cares about chairs and persons as objects. It doesn't care if you're a human being or a chair. The situation is the same. Yes? So in this problem, you can imagine that I keep the students here and put chairs on their head. But for some reason, you don't want to believe that. That's the same story. Yes? Okay, if you don't like that method, the answer is the same. But here I have student number 1, student number 2, up to student number 30, and then I have chair 1, chair 2, up to chair 30. Up to chair 5. So, the stage 1, I would tell assigning a student to chair 1. Stage 2, I would say assigning a student to chair 2. So in how many ways a stage 1 can be done? I have 30 students, I want to assign one of these students to a chair. So I have 30 options available. And again, assigning a student to chair 2, because chair 1 is occupied by one of them, so now I have 29 students available, so there is only 29 students. So the same story happens. But psychologically, I don't know, people are more comfortable to understand this rather than understanding this. I want you to understand that mathematics doesn't care if you're a human being or an object. Yes? So we are objects. Yes. So there are two things that I want you to understand here. So first of all, this human nature of the way that we think. And the second thing is that this problem was extremely simple. This is E-level question. But if you don't used to tell those stories that I emphasize so much by defining your task and defining your stages, immediately it becomes unthinkable. You don't know what to do. Okay? So try to actually emphasize on this. Any questions? Okay, thank you very much.